All right, hello class. This is the first time I am recording a video of me working out a math problem, so bear with me if there are any technical difficulties, and I apologize if the video is a little shaky. I'm using some contraption to keep my phone elevated so that I can write. So today we are talking about related rates. And I do want to let you know that we will revisit this next week as well when I am in class to help you with questions you have, clarifications, and that this is a really difficult topic. So if you're struggling with it today, that's okay. What I ask is that you write down specific questions you have and fill out the Google form so that over the weekend I can adjust the instruction for Monday to suit all of your questions and get out those answers. So with that said, let's dive into our first related rates problem. Okay, an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. If the distance between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when their distance is 10 kilometers, what is the speed of the plane? So the first thing I always do is I read through it once, and then I read through it again to underline and highlight key information. So I have an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. If the distance between the airplane and the radar station is decreasing, that's important to at a rate of 400 kilometers per hour when their distance is 10 kilometers, then the question is, what is the speed of the plane? In related rates problems, it is pretty much impossible to do them if you do not draw a diagram. So the first thing you want to do with every single related rates problem is to draw a diagram regardless of the context. This does not mean you need to be a good artist. For example, this little box here is going to be my radar station. It is on the ground. It's important to label the aspects of your diagram as well to remind yourself when you're going back and reading through the problem where certain things are. So we know airplanes, that's my little airplane, are in the sky, and it says it's flying towards the radar station. So I know it's moving in my diagram to the left. It says the airplane is at a constant height of 6 kilometers above the ground, so that is 6 kilometers. And I do know that this distance right here is perpendicular. Let's shade in the radar station. That way we don't confuse it with the right angle. So I know this is a right angle because when we measure this constant height above the ground, it needs to be perpendicular to the ground between the airplane. Next piece, so I've done that. If the distance between the airplane and the radar station, okay. So before I get here to the decreasing, I want to talk about where is the distance between the airplane and the radar station. So for some of us, we might be thinking, well, that's going from horizontal and then downward. But that's not a direct distance between the airplane and the radar station. When we say distance between two objects, we mean the shortest distance. So that would be the diagonal distance. And instead of calling it capital D, I'm going to call it R for radar station. We know this distance, R, is changing because the airplane is flying left towards our radar station. And we were told that the rate at which this distance is decreasing, since it's a rate, we're going to say the derivative of this distance, R, with respect to time, is decreasing, so negative at a rate of 400 kilometers per hour. But it doesn't say it's decreasing at a constant rate. It says when their distance is 10. So when R equals 10 kilometers. what else can we label in this diagram? Well, we do want to set up some sort of variable expression for speed of the plane. So speed of the plane, if we're thinking that we're in this little airplane and we are moving to the right, to the left. Well, this direction right here, I don't know, what do you want to call it? The place, if the airplane is now here, that would be x of some t. We'll use x of t for position. X of some t. And then over here, it's getting moved even closer to the radar station. It's x of t2. Call it t1 and t2. So this distance, we'll call it x of t, the position of the plane. So we're thinking about that position of the plane as the horizontal distance. Horizontal is important here. The horizontal distance between the plane and the radar station. Well, I know that speed is the absolute value of velocity, and velocity is the derivative of a position function. So if I'm thinking about speed of the plane, what I'm actually trying to find here is what is dx dt when r equals 10, because it's still asking for when the distance is 10 kilometers between the two, what is the speed of the plane. And just a quick jot down that this dx dt, what units will it be in? Well, it should be units per time because we're in speed. And this plane is moving, since the distance r is in kilometers per hour, we will assume that we will also measure the speed of the plane in kilometers per hour. Okay, I think that is all that we need to set up the problem, and now it's time to do some math. So our first steps in drawing the diagram, again, were literally drawing the scenario out. We drew the radar station, we drew the ground, we had the airplane, and then we started to go piece by piece into the sentences. We even broke sentences apart to start labeling distances, r, writing the descriptions like the rate of 400 kilometers per hour as a derivative. We labeled another aspect of this context, the position of the plane, in order to write what we wanted as a derivative. We are in calculus, so we will want to be using derivatives to solve this problem. So now that we have information in calculus terminology, we can start to set up a relationship. So let's check off this box. Do we label all places in the diagram? Yes, with variables, and we defined the variables to make sure we know what we're talking about. We expressed our givens in terms of those variables, that negative 400 kilometers per hour that was given to us. This 6 kilometers we put in, that was given to us, and the r equals 10 was given to us. And the what do we want to find is kind of a given in terms of what rate are we looking for, or what value are we looking for. So now it's time for the math work to answer the question. What is the speed of the plane when the distance between the plane and the radar station is 10 kilometers? So again, I said we want to set up a relationship because these are called related rates. Related meaning we want a relationship between all the aspects of this context. So the trick here is to look at your diagram and try to notice a couple of things. What do you see is going to relate your X, T, your R, maybe the 6. Well, the first thing I can note is that this pink distance here, since it's parallel to the ground, I can call this also X of T. Like that position here, those should be equal. So this can also be X. And when I put that down here, that helps me see, oh, I have a right angle, I have a distance here, I have a distance here, and I have this diagonal distance here. When I highlight those 3 pieces, I see not just any old triangle, but a right triangle. And in your previous math classes, you have learned a lot of tools about right triangles that can help you solve for both angles and missing side lengths. So I'm gonna redraw my diagram here, but just with the pink triangle. So I have R, I have 6, and I'm just gonna call it X. What tools do we have for right triangles? So if I'm gonna brainstorm tools for right triangles, that might be helpful. The first thing I think of is, because we're about to teach this in geometry, is the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. The second thing I think of is trig. If I have an angle, I can use sine, cosine, or tangent, or I guess I could use other things as well to find either missing angles or missing sides. I can use inverse trig as well. I am separating inverse trig and trig because one, trig we use if we have the angles, inverse trig is if we want to find the angles. And when I'm looking at my diagram above, well, I don't see any angles given, so we're not going to use trig and we're not going to use inverse trig. So that leaves us with the Pythagorean theorem. And we will set up a relationship. Leg squared plus leg squared equals your hypotenuse squared. I'm trying to think about what color I want to use. Because let's color code. Okay, let's make X green and R blue. It was blue above. Something that I will do with almost all of my related rates problems is color code as well. So that might be a good tool for you. So we have R squared is equal to 6 squared. Got to get all the pens ready. Plus X squared. And if you notice from above in the diagram and the descriptors, we want dx dt. We have dr dt. We also have a value for r. So because we have dr dt and dx dt, or at least we want to find this, that tells me that I need to take the derivative of this equation. And really what I need to do is I need to do implicit differentiation on both sides with respect to time. R, that distance between the radar station and the plane, is a function of time. The position of the plane is a function of time. Is 6 a function of time? Well, we'll get back to that. So the derivative of r squared with respect to time is going to be 2r dr dt, chain rule, equals 6 squared. What's the derivative of 6 squared with respect to time? It's a constant height. We have that from above. It's a constant height. So our derivative of this piece is going to be 0 plus the derivative of x, the position of our plane, with respect to time, 2x dx dt. Cool. So we're making progress because we have r from the givens. We have dr dt when r equals 10. We want dx dt. And so in this equation, the only still unknown value is that x. Just a reminder, we want dx dt when r equals 10 specifically. So because of this, we can set up a secondary equation, still using the Pythagorean theorem, when r equals 10. 10 squared equals 6 squared plus x squared. What must be the position of the plane with respect to the radar station when the distance between the radar station and the plane is 10? 100 equals 36 plus x squared. And for those of you who recognize that this is a Pythagorean triple, x will equal 8. So we can plug this 8 kilometers into the equation here. Because we want when r is equal to 10, we can plug this one into here. And from above, let's see if I can, we can take this negative 400 and plug it in to our rate right there. So we wind up with 2 times r is equal to 10. When r is 10, the rate is negative 400 equals 2. When r is 10, x is 8 times, we still don't know what dx dt is. We still don't know what the rate of the plane is. So 2 times 10 is 20 times negative 400 is, well, 2 times 4 is 8. Negative 8, 1, 2, 3, 1, 2, 3. I think I did that math correctly. Is equal to 16, 2 times 8, times dx dt. Isolate for dx dt, divide by 16 on both sides, and we should get negative 500 equals dx dt. Whew. So we've got what dx dt is. The last piece of a related rates problem is to write a sentence to put this number into the context. So what is negative 500? Let's make sure we actually answer the question, what is the speed? The speed of the plane is, speed is the absolute value of velocity. So it's 500 kilometers per hour. And then in what direction is it going? Well, as the plane is going towards the radar station. So going toward the radar station. In this diagram, it's moving left. In this diagram. Check your units. Check that you actually answered the question, speed of the plane. We should add on that, what is the speed of the plane? Is it always 500 kilometers per hour? No, the speed of the plane is 500 kilometers per hour going toward the radar station when the distance between the plane and the station is 10 kilometers. Because we don't know if the speed is constant. What we do know is that when the distance between the two is 10 kilometers, the plane is moving at a speed of 500 kilometers per hour. And that concludes our very first related rates problem. Thank you for hanging in there. Please write down questions you have so that I can answer them on Monday. I will be here tomorrow, well, your tomorrow, Friday, during Flex to answer all sorts of questions. And please come with specific questions and comments. I hope you are having a great day. Goodbye.